Hi, everyone. Thanks for joining us on this beautiful Friday. Just a few announcements before we get started. If you're registered for class, please sign in. And next week, please join us for lightning talks in our newly remodeled room in rate 221. We're really excited, and students will be presenting posters that they're going to present at PAA later. So we really look forward to y'all coming and giving everyone feedback and celebrating their work. Without further ado, I'm going to hand it over to Dr. Rachel Heath to introduce our speaker, Jason Kerwin.
Hey everybody. So thanks Jessica and CSDE for allowing me to introduce Jason. He's my new colleague in the economics department, and we're so glad to have him and Audrey joining us at UW here this year. So, we're very excited to have Jason in particular, not just because he has an amazing collection of shirts that I always like to hear about and hear the story behind, but he's a fantastic colleague as well. So Jason studied in undergrad, he studied physics and international relations, which I think is actually the perfect training to become a development economist. That kind of intersection really summarizes kind of the breadth of what we do. So he worked in the private sector for a bit and then went to grad school at Michigan, did a PhD in economics where he was a trainee at the Pop Center there. So he comes well-versed in the demography tradition. Then he went to University of Minnesota as an assistant professor in the, if anybody knows economics, not the econ department there, which is quite the place, but the applied and ag econ there, and then ultimately became an associate professor, and as I mentioned, started here at UW this year. So he does a lot of research on both health and health and education in low-income country settings, and a lot of just very, very cool data collection. I do field research myself, and Jason just does he just does it in such interesting but challenging settings. So today he's going to talk to us about, eliciting subjective probability distributions. That's a very challenging thing to do. Jason does it so well and interestingly, a lot of long-term follow-up to educational interventions, and it's always hard to track down people after such a long time, but it's just so valuable to know if we had an intervention that, looked really great in the short run. If you go, to all the painstaking work of tracking them down 10 years later, do we still see those effects? And thanks to Jason and his co-authors, we're starting to kind of get evidence on things like that. So that's just some of the very cool research Jason does. I'll let him tell you firsthand about this project.
Great. Thank you. Thanks for the nice introduction. This shirt, by the way, is from my hometown of Kaimuki on the island of Oahu in Hawaii. Okay, great. Is there like a place I have to stand? I have to be right there the whole time? Oh, okay. Well, I'll try. I mean, I like to wander, but I guess I can't. So, okay, carry this around a little bit. Yeah. All right. Anyway, so cool. I'm going to be talking about navigating ambiguity. This is joint work with my grad student at Minnesota who's just finishing up. She'll be a postdoc at UPenn in the fall. Give is great. So the core question in this paper is about whether you can be uncertain about a probability belief. So I want you to think about two probabilities of things that might happen. One is the chance that you roll a 6 on a single die, right? Like a regular 6-sided die. What is that probability? 1 in 6. Okay. And then, this one was selected for the last flu season, but what's the chance that you'll get the flu in the next 6 months? Anybody want to give me a guess? Something like 1 in 6, right? I mean, I used to have these calibrated to be something like the same number. Which one are you more sure about? So if the die, there's ways to check that a die is fair. You can find fun YouTube videos about this, and they don't, you just have to have like sharp angles on all the corners and then not have the weight distribute in a weird way, and then you can guarantee that it's actually 1 in 6. And the chance that you get the flu in the next 6 months, it depends on a lot of things. So is it like a bad flu season this year? Did you calibrate the vaccines well? Do you get a vaccine? You know, like other random fluctuations and stuff. And the kind of point here is these are both probabilities, but you should be fundamentally less sure about the second probability, even though both of these can be expressed as like a chance out of 100 that a thing happens. And it's a little bit unusual to think about uncertainty in probability measurements. So in a standard, okay, EU is expected utility framework, but it doesn't, you don't really need the expected utility part. We typically think that the probability mechanically determines the level of uncertainty. So there's a Bernoulli distributed random variable. So just take a thing that you do once and it has a chance of happening or not, right? Then the probability, if the probability is 0.5, the standard deviation of that like distribution is 0.5. And if the probability is 1, then the standard deviation is 0. And you can do the same thing for a probability of 0, right? So like if there's a 0% chance of the thing happening, then you're also like, there's like 0 sort of variance in the outcomes. And you can just graph the standard deviation against the probability like that. And so a lot of social scientists who've thought about these like subjective risks and so forth, maybe especially economists, but maybe other people as well, carry around this intuition that if there's like a probability of a thing happening, that captures all the uncertainty. And by the way, please do like raise your hand and ask questions or do the raise hand thing on Zoom or whatever, because I will run out of things to say if I don't get enough questions. But then we can all leave early, so I don't know. All right. Our paper is about measuring uncertainty separately from the level of people's risk beliefs. That's what we're gonna try to do here. And the reason this matters is that people make decisions based on what they think is true about the world, right? So in the history of like modeling decision-making in economics, we have historically just said, you know, back in the day, we just ignore expectations about the future. People react mechanically. Maybe you can like trick them, tell them something's true. The classic thing that we tried to trick people with was like inflation. So you like sort of, you can goose the economy by like injecting more money and then everybody like, you know, thinks that they're richer. And then there was this rational expectations revolution. People associate largely with Bob Lucas, where we said, oh no, people have correct beliefs on average. And that's like obviously nonsense because people don't know lots of things about the world. There's all kinds of things like about this room that I don't know, let alone like everything in the world. I'm certainly not right on these on average. And so Mansky's approach to this is to say, look, what we should do is try to measure what economic agents actually believe. Like, what do people think is true in the world? And then sort of use that to inform, you know, how we analyze data. And so sort of since then, and maybe even starting before that to some extent, we have shown that we can measure subjective beliefs and they matter quite a bit, right? So there's a long history of measuring beliefs about what's going to happen in the future with economic variables in rich countries. You can also make these kinds of measurements of subjective beliefs and subjective risk beliefs in developing countries. And so there's like a sort of literature on this that you could think of this paper as being part of that goes back, you know, at least 15 years. And that's true, even though people have a lot less formal education, there's like low rates of literacy, there's low rates of measured numeracy. It's a cool new paper that we should cite in here. It came out in Nature, I think, showing that people might not be able to like pass a math test, but they can do the kind of math they need to like buy stuff at the market really well. And then these subjective beliefs matter for all kinds of different stuff, especially in the domain of health, right? And so there's this literature that I've written papers in about like how people decide, you know, what to do with their sort of sex lives and also their fertility and marriage choices based on the risks of HIV. There's research on like water safety and where people are getting their water from and also where people decide to live. All of these things depend on what people think risks of various things are. And it's also it's also true that these beliefs are frequently uncertain, right? So if you think about your beliefs about your real earnings next year, those obviously are going to depend on a bunch of stuff. And obviously you should have like an estimate of what your real earnings will be and some uncertainty. I think that uncertainty has just gone up a bunch, right? So like seemed like inflation was falling. Now maybe it goes up a bunch. Your real earnings, depend not just on like whatever like is technically inflation, but also on like the prices of the goods out in the economy. And so if we jack up tariffs on those, like, if like 3 days ago tariffs are going up, then like your real income goes down. If those get canceled yesterday, then those go back up, right? You might not get a raise now. Maybe you thought you were gonna. You might lose your job. You might be put on furlough. Turns out we found out here. And so those things happen, right? And they can happen in unexpected ways. You can elicit uncertainty about earnings beliefs by asking for some plausible range of earnings, or just telling somebody like your earnings could fall somewhere in here, and then having people put probability mass on different values. So you could like have them like kind of fill in a histogram. And that's like a completely intuitive thing to do, right? And in fact, studies have been doing this now for decades in rich countries, and there's even some data that's done this in the developing world. So it can be done. It's like less obvious what exactly you would do for a probability belief. The probability already is like a probability. You're going to put probability mass on the probability. Turns out you can get people to do that, at least, if they know a decent amount of math. And we are going to, so there's like a bit of a lag when I click. So I'm just trying to, okay. So we are going to sort of figure out a way to do this and then show that kind of works. So in previous work, we've sort of shown that we can model and measure uncertainty about probabilities in general. And uncertainty about probabilities is like kind of an old concept. So you might have heard of Knightian uncertainty. Ellsberg has work on this, right? These are prominent, sort of famous papers. There's not a ton of empirical evidence on this. So there's imprecision in probability beliefs. There's like sort of meta uncertainty. We'll come back to what we call this. In lab experiments, a lot of people, if you ask people one of these probabilities, they keep it some round number, which is suggestive that they do not actually know what the number is. They're just sort of giving a ballpark guess. If there's like a probability you ask me and I actually know the probability, then like I can get it like right on the nose. And if I'm not sure, then I just sort of like, maybe about 20%. And you can use that rounding to back out how much imprecision there is. Right. So some people, if you ask them about a probability, will just spontaneously volunteer a range. And you can like record that. And you can prompt people for those ranges. And then there's a correlation between like the range that people report and behaviors, risky behaviors, when it comes to COVID-19 risks. That's a study from, I think that's from the UK by Adeline Delavande and co-authors. And then there's like, other domains. So my former grad school classmate, Jess Hoyle, and some of her co-authors have done some measurements in like, what's the probability that this fertilizer is fake? And like the higher the imprecision in that, the bigger the range, uncertainty in that probability, the lower people are willing to pay. And that's like a standard way of sort of modeling decisions. People are like pessimistic, right? So I say the range, the probability could be anything from 1% to 30%, and one of those is like pessimistic. I go with that. And then there's this related concept of cognitive uncertainty, and that has been shown to affect the updating of risk beliefs. Yes.
Good idea. So like, we go back to the flu example. You're asking me, like, I'm not even sure like what the language you would ask me, like, assume I'm just mathematically sophisticated. That may or may not be true, but like, like, are you saying like, what's the probability that this is the probability that you get the flu?
That is roughly what they do in the cognitive uncertainty papers. So they sort of like, oh, sorry. So the question for the, 27 people who are on the internet is like, like, how would you even ask these questions and how would you frame it? I mean, I think that that is a confusing thing to do. That's like hard to implement in surveys, and thus I've like never tried. So I'm not going to do that in this paper. But one thing you can do is be like, okay, you said the number was 5%. Now, like, let's say that like there's like 4 to 5% and 5 to 6%. And then in Enki and Graeber, what they do is have people like put probability mass like in those ranges. And then I guess outside of those ranges. And again, so it's like kind of a meta probability. What's the chance this is the real chance? Like, and then you want to think about this as like, oh, that's like the kind of number you could like look up in a. So it turns out that there is like a fact of the matter about the probability of contracting HIV from an HIV positive partner. Like if you can condition on like condom use and like stage of the disease and so forth. So you could go look that up. Like, yeah, that's like, I don't know, how much would you gamble on it being in those ranges or something? Okay, so I've mostly been calling this imprecision. It's unclear what we should call this concept. We focus on the phrase imprecise probabilities because that's what Chuck Mansky told us to do. That's what he does in his paper, and like there's a literature in statistics where that's what they call it. But like sometimes people call it ambiguity, sometimes they call it Knightian uncertainty. And the fact that people use all kinds of other terms and then also this cognitive uncertainty thing that's like kind of related makes it like very confusing to even see what the other papers are like in this literature. What we're talking about, again, is the magnitude of uncertainty about the probability of an event occurring. So like, how sure are you that the actual chance is 5%? And every term basically has drawbacks. Ambiguity gets used to mean all kinds of different things. And then, so often when I like talk about this, I say ambiguity, people are like, oh, like cite like 1 million papers about ambiguity aversion. But like, that is typically a distaste for unquantifiable uncertainty. So like, you just have no idea what the probability or the distribution is. And we are like very specifically going to quantify this. The problem with calling it imprecise probabilities is that it makes it sound like I'm just measuring these wrong. And I don't think that that's what's going on. And yeah, so there is a distinct issue of mismeasuring beliefs. And in fact, almost for sure, everything in this data set is mismeasured and in every data set to some extent. But I think that there's more than just measurement error happening. Okay, so what we do here is examine how imprecision affects the updating of risk beliefs. We use data on imprecision and HIV risk beliefs from an RCT that I ran in Malawi in grad school with baseline and end-line measures of the levels of risk beliefs and imprecision in those beliefs. We're going to characterize how imprecise those beliefs are. And then we're going to use the randomized information treatment to look at how belief updating depends on imprecision and also other things. So you can think of like, we have the prior, we have the posterior, right? We have the data. I feel like the thing that you tell people is like less clearly named than those other things. But we have the thing that we tell people and we look at how much people update. And in fact, they do not update fully, which they probably shouldn't. And they also don't update like standard Bayesians. And the updating that they do depends on how imprecise their priors were. And we think that this contributes to the literature on measuring the beliefs that shape people's behaviors in a number of ways. So one is that we show that these imprecise probabilities can be measured in a developing country setting with low rates of like low numeracy, low rates of formal education, which fits into this literature on, you know, just measuring subjective beliefs in general, and then specifically in the developing world. There's substantial imprecision for a very well-known problem. Everybody's aware of this. Everybody knows the basics of like how it's spread, like how to avoid it. Like 100% of the sample correctly reports that like using a condom reduces your risk, for example, right? And it's a super high stakes problem. So about 1 in 10 people, like adults in Malawi, have HIV in the region that we're in. It's more like 1 in 5. And it's just, you know, it's an important determinant of things like mortality and then the rest of your life course. There's a really interesting work on this by Jenny Trinidopoli, where she basically looks at like how HIV and the uncertainty around it shapes people's lives. And so if you think about like other things, well, there's research on this with dementia. That's, you know, everybody who's getting older should be like worried about dementia. It's definitely an issue. The COVID-19 study is pretty different. It's early in COVID. That's where the data is from. And, you know, people didn't know about it as well. And then it kind of fits with this fertilizer paper as well. There's an adjacent literature on continuous variables. And then there's this rounding business. And then there's the updating thing, right? So how do people like basically form the beliefs that they hold? And there's a paper by Adeline Delavant on this. There's the Enki engraver paper that's like sort of adjacent. And there's not a lot. And then finally, we're going to show that the imprecision levels that people have shift in response to new information. So under certain conditions, if I tell you new information, it's actually going to make you more sure about what the sort of fact of the matter is. And in other conditions, it's going to make you less sure. All right. The data comes from Southern Malawi, and it's about HIV risks. Just to like sort of fix concepts, Malawi is this country here. It's like nestled into the fishhook shape of Mozambique. It has the 9th highest HIV prevalence in the world. And, you know, all of the places with the highest HIV prevalences are down here in Southern Africa. It's very economically underdeveloped. So it's the 8th poorest country in the world. There's low literacy rates and rates of formal education. The data was collected for a study of fatalism in response to HIV risks. So this is a randomized field experiment that told people the true rate of HIV transmission. The focus of that paper was that we have a sort of scared straight approach to a lot of diseases, and HIV is one of them, where the government policy is more or less just to tell people that the risks are super high, and then this encourages better behavior. And in that study, I show that for key populations, it really does not. It backfires very sharply because people give up. This was a probability sample of an area in Zomba district in southern Malawi called Tia Mwambo. So I sort of randomly sampled 70 villages, and then I rostered everybody, and then randomly sampled 1,300 people from those. The villages are randomized to either the information treatment or control. After follow-up, and most of our analysis is going to be on the sort of subsample that has the follow-up data. We're slightly skewed female because, so we started 50-50, it was stratified on gender, and men are less likely to just be around when we come look for them. Mostly married, the mean age is 29. The average person didn't finish primary school. The belief variable here is the annual risk of HIV transmission. And so it was collected in this form. If 100 women who do not have HIV each have an HIV positive sex partner for 1 year and do not use condoms when having sex, how many of the women do you think will have HIV at the end of the year? And then they give a number, and then we convert that into a probability by dividing by the denominator. And then we do this thing here, kind of adapted from the HRS, which is a lot of people will keep at 50 because they're unsure. And so we know their original report, and then we also got their best guess if they were just expressing uncertainty. We do a little analysis of that particular keeping pattern in the paper. We have similar questions for other risks as well. So we ask the same thing for per act risks, for condom protected risks for both versions. And then we have prevalence questions, although those are out of 10 rather than 100, I think. I have to go back and look. The questions are gender specific. So this is the female version, and this was asked to women, and then there's a male version that was asked to men. Baseline risk beliefs are incredibly high. So the baseline belief about the annual HIV transmission rate is like, you know, for 80% of people, they say you're going to get it for sure. And in fact, if you look at the per act risk, people also, I think 60% of people say that's for sure. All those people are going to get HIV. There's this paper that we wrote, sort of a companion paper to, or me and another student, about enumerator effects. We can adjust for those. It doesn't affect anything in here. So what is the right answer to this question? So this is the annual rate of HIV transmission, conditional on one partner being infected and the other one not being infected, and no protected sex acts. And for context, like typical couples here would have sex about 100 times a year. Anybody know? Yeah, it's 10%. And this is true of a lot of diseases, is that people like really skew high on what they think this is. So there's a really, I talked about the fatalism paper. There's a paper about fatalism and COVID risks where like everybody's like way kind of overstating what they think the risk of COVID transmission is. And then like that doesn't induce them to be careful. They're all just sort of give up. And then this sort of lab experiment that these other folks did, they told a bunch of Americans, like, actually, this was COVID classic, so before Omicron. If somebody in your household comes in with COVID, like, what's your chance of getting it? The actual answer is like 1 in 4, and people thought it was 100%. And I think what they were telling people is like, what's the R naught? And again, people were skewed very high. And in fact, if you talk to doctors who are not specifically infectious disease doctors, they have the same priors as Malawians. I don't know, that's anecdotes, but that's what I've seen. Okay, so our imprecision variable is based on asking for probability ranges. So what we basically do is say, okay, if the answer to this is not already 100, could it be more? If so, what is the most women out of 100 who you think could possibly get the virus in this scenario, right? And then people can say it could not be more, in which case we sort of, like, let's say that the answer they said was 90, and they say, no, it couldn't be any more than that, and then we would sort of plug in 90 in like how we construct this variable, and then do the same thing for could it be less, and again, that's kind of bottom coded at 0. So if you start at 0, then you're sort of at the edge of the range. We don't ask this question. In contrast to most previous work, we elicit probability ranges for all respondents. Some other papers do this. Our imprecision measure is just the width of that range. So that's what we're going to work with. We're going to express it in percentage points, just like the original probability. And then we can try some other definitions, and it doesn't matter. The information treatment is telling people the true transmission rate, which is 10% per year. The treatment explained the source, which is the Malawi National AIDS Commission. And then the underlying research paper, which was a study in Uganda. This was verbal information supplemented with graphics. And the new information leads to large reductions in risk beliefs, right? So these are the posteriors, what we measure at end line. The control group is like sort of about the same. The treatment group is shifted downward, although not everybody sort of updates, right? Some people are updating to about what they were told the right answer to, but not everyone. And there's updating of other beliefs as well. What does imprecision look like? So imprecision is low for most people. Most people tell you a number and they're sure of it. And in fact, most people just tell you the number is 100% and they're sure that it's 100%. Done. But this is not restricted only to people who report 100%. Some people say, it's 90% and they're sure of that. And then there's a long tail. So there are people, to get a number like this, since no one's prior was that the rate was 0, you have to say you think the risk is 100%, but it could be as low as 0%. And so there's this long tail. There are people who express imprecision. And this has an inverse U relationship with the level of risk beliefs. Some of this is mechanical, so you cannot express so basically you can go all the way down to 0, but you can't go up at all if you're at 100, right? But what we can show is that there's kind of two sides to this, right? There's sort of the upside and the downside, right? So how much higher could it be? How much lower? And actually, look at the people at 100%, right? How much lower they say it could be is also smaller on average compared with people who are toward the middle. So there's a real actual connection here. And then when we do our data analysis, we have to adjust for, we're going to have to control for annual risk beliefs, and we're gonna have to do it non-linearly because it's not a linear correlation in order to get the right answer. There's no clear connection with numeracy here, so these are sort of dot plots with the red lines show the averages, and it's just uncorrelated with measured numeracy in this setting. Also unrelated to education. we try this with age and like a few other things, and it's pretty uncorrelated with those covariates. So on the one hand, it's like a little bit weird because you'd expect, you know, some of these things to affect how sure people are. On the other hand, it's helpful for some of our empirical work because it means we don't really have to control for this stuff, although we do. Yes.
But there were differences by gender, right?
So what do we see on gender? I can't actually remember.
This one is that.
So hang on. I need to check. Certainly those distributions are not literally exactly the same. I don't know if we can get the equality or the equality. It looks like the males are higher for sure. So one thing that we tried doing was just regress imprecision on every covariate we have at baseline, or use the lasso to pick covariates. The lasso picks nothing. It just literally picks 0 variables, meaning everything's getting shrunk to 0. Okay, so one thing that we verify from the literature is that there is this correlation between basically rounding, so reporting a round number divisible by 5 or by other things, and the level of imprecision. And so, if you want to think about this, anything that's divisible by 5, that would be 0, 5, 10, 15, whatever. And that's dominated by the mass point at 100%. So then we could say, well, what if it's divisible by 50? So then we're sort of pulling out the average for those. Those people report less imprecision because a lot of them are at that 100% mass point. And then if we look at the sort of columns where we, say, what is the difference for people who have a average risk belief that's divisible by 5 that are not in the 0, 50, or 100 category. Those people have higher levels of imprecision. And that's robust to playing a little bit with that thing where we nudged people who are on 50 to report a different answer. Okay, so now we're going to talk about updating. So we're going to do a little bit of theory using a standard Bayesian model of belief updating. So the priors here are going to be represented by a beta distribution. This is the conjugate prior for the Bernoulli random variable, which means we're going to get another Bernoulli out. I think I can't remember the details of why we care, but this is what people do. So what we're going to do is basically define the alpha and beta here, the number of successes and failures that people have observed before, or that are implied to have been observed by their prior, which is just a number. And what we're going to do is define mu, which is just the expectation, right? So that's going to be their average risk belief. And then nu, and nu is related to the variance, but it's not the variance. So basically the variance depends on this thing that looks like how we define the standard deviation of a Bernoulli random variable, but it's also multiplied by this new thing. And then we could say, what if we raise the dispersion of priors? So basically, what we're going to do is work out what are the posterior values of mu, which is the expectation. So that's going to be the actual number that people report. And then nu, which is related to the range they put on it. And here's what those posteriors look like. Belief updating is just we could think about this as the derivative of the posterior expectation with respect to X, which is the new data that we're giving them. And in particular, what we care about is the risk in the new data. And what we find is that it has this form. What we care about is how does that change with higher dispersion? And we can work out that we get an expression that's always positive. And so we would predict more updating if nu is greater. And so here is a graph, because I find all that hard to follow. So what we have here is the blue is the prior in both of these graphs. And one, we have a more diffuse prior. So it's people are less sure. And here it's a sharper prior. And then the posterior, red, that's how much people update toward the true number, which we're telling people is 0.1. right? And you can see that the amount of updating is larger with the wider spread. Yeah.
I know you were using the word likelihood here, but the information in likelihood.
So is the I'm not an actual Bayesian, I'm just trying to use this stuff. So is the likelihood like the data, like the thing that I told them was the risk?
This would be true, but under a case where you have, I think what you're telling them is less imprecise than, or more precise than the thinnest trial.
What if, so the question is like, what if the likelihood
What if you
has higher imprecision than the prior? Is that the idea? So the actual thing that we told them was just like a number and a number of cases, but I guess like the number of cases determines the precision. Was there another question? Oh, sorry. The question is, isn't this result dependent on the likelihood, and in particular on the likelihood having higher imprecision? Like what if the likelihood had higher imprecision than the prior? I think we can work that out from the number of people. So what we told people, this is partly for simplicity because the way that the epidemiologists like collected and reported the data was like a little confusing. We just said, hey, there's like 100 couples and here's how many. In fact, there's like a little bit more than 100 couples and they observe them from multiple windows and stuff. But like what we're telling them is like essentially like the denominator is 100. So total successes and failures is 100. As I think I can work this out. I think. So that actually might help with like other theoretical mysteries because this model doesn't fully work and then other models that we've tried work worse. Okay, so we're going to try to validate that basic prediction. I've alluded to the fact there's other predictions we can get out of it that don't make any sense. And then we tried something that's designed for imprecise probabilities, and it also kind of gives like results that don't make a ton of sense. Okay, so what we're going to do is estimate treatment effect heterogeneity by imprecision in people's probability beliefs. And so the sort of thing we're trying to estimate is HIV risk beliefs at n line for respondent I, right? And here's their baseline beliefs. We have a treatment, it's the information treatment. What we want to know is beta 4, right? How does the treatment effect vary with people's, like the imprecision in people's priors? Imprecision is correlated non-linearly with baseline beliefs. So we need to control not just for baseline beliefs, but also by the treatment effect or for the treatment effect heterogeneity by those beliefs. So we're going to do that in a sort of, we're going to have like a linear version, and I'm also going to show you one where I break it up into 3 categories. We're also going to test robustness to controlling for other X's and their interactions with treatments. That doesn't matter a lot, I think, largely because there's no, there's not much in the way of correlation there. Yes.
Just to make sure I'm following. So, you talk about keep updating. I mean, I would think usually that you have some absolute value, like it would either be up or down. But is this, do you just have the straight beliefs here because everybody's so pessimistic, and so like essentially the only way they're updating is down, or am I kind of misunderstanding kind of what you mean by it?
So well, what would you want us to do? You want to know whether YEL is like higher or lower? Is that the?
I just naively heard you say updated.
Yes.
Like, I would have thought like the left-hand side variable like changed in your like recorded.
So abstract, okay, if we abstract from this interaction term, like there's versions of regressions that don't have it. So that would be equivalent to this, except imposing that beta 3 is 1, right? Because I could like subtract that from both sides. And under the condition that beta 3 is 1, and that would be the same. So we could try it though.
Yeah, and I guess it's not exactly the same as not controlling for the baseline and putting the change. But sorry, I missed that.
So delta, yeah, so delta Y, we could do that. I think we're still getting like conceptually like the same thing, at least in terms of like, you know, like direction because we're basically looking at how the treatment, like, how does the treatment affect your posterior, right? So we have a control group that doesn't get the information treatment. And like the idea with the control group is we're like picking up other things that might like move this around. Right. So there's versions of the regression that don't have this interaction term. And so those ones can be framed as like sort of change version of this if we were to impose. But anyway, like I can just try it and look. I don't think, yeah. So I think the reason to not focus just on the change is that like the control group has like evolution in their beliefs as well for like whatever reasons, right? They like learn new things. There's those enumerator effects that I talked about. So those are gonna, for reasons explained in that other paper, they show up in the end line for everybody. Okay. So one of the key results here is that imprecision predicts more updating in response to the new information. So what we have here, this is just the controls. What we're looking at is the treatment by imprecision term. And so, you know, that is significant and negative. The sort of main effect of the treatment is also negative because this is like, you know, lower than the likelihood, which is what I should call it apparently, is lower than people's prior. And you can sort of work out how big this is. It's not a massive difference. So like, you know, for like the average person in our sample, this is like augmenting the main effect by about 10% more. Or if you do like a one standard deviation change, it's about that magnitude, but it's there and it matters. The other thing we can look at, oh, yes. Yeah, you're muted. Maybe you can unmute or. I can see her, little window here. Did you put something in the chat? Chat. View and respond. Well, we can, you know, we can, I think I'm almost done with the slides. So then like you can ask it at the end if you figure it out. Or email me or whatever. Okay, so another thing we can estimate here is how this new information treatment, oh, yeah, it was great. How does this information treatment affect imprecision levels, right? And, you know, the sort of simple answer here is that it really doesn't, right? So we can't reject the 0. It looks like there's maybe higher imprecision on average. This is I think I worked out an intuition for what this should do. I cannot quite match it to the model, but here's like the argument. It's like, if I come in and I tell you, you're right, Jason, you knew this number and here's evidence for your prior, then you get more sure. If I come in and I tell you, look, here's the right answer, right? It's very different from what your prior was. Then like you might update toward this to a certain extent, but I think you also should be less sure, right? So what you've been taught in school, what you've been hearing from like medical professionals and public health authorities is quite different from what's like, you know, apparently posted on this website and validated by the scientific research. So someone is wrong, right? And now I feel like your overall sort of uncertainty about this probability should go up. And so this is kind of like what we look at here. Okay, so panel A is just like breaking down the like effect on people's level of risk beliefs by like where they are in the prior distribution, right? There's larger updating for people with higher priors, although we can't project that like this cell is the same as those. These are significantly different from that one. There's more updating the higher your prior is because it's like the information's newer. We do the same thing for people who have But we do the same thing for how the treatment affects imprecision and break it down by where people are on the sort of, in terms of their priors. What we see is an insignificant effect for people with low beliefs. So not quite what I would have expected. I would have expected like a reduction for them, a reduction for people in the middle. And then people at the high end, their imprecision actually goes up. And that last point does kind of match my intuitive model of the world, although nothing that I can work out from any of these Bayesian updating models, right? So these folks were sort of told this like totally like wild new information. It's nothing like what they thought it was. They thought the risk was 100%. You're telling them it's 10, right? They do some updating, right? They do a meaningful amount of updating, but they also become less sure about what the right answer is. Their range goes up. And then there's this whole thing with like, is the range capped off? So we have these robustness checks looking at like, what if we just use like half of the range, whichever is wider, and then do some cop coding on that and stuff, and everything goes through. How does this compare with the model? So there's two key comparative statics. We have this prediction of more updating if the imprecision is higher. We don't really, we do confirm that. The model, every version of the model I've tried, predicts no effect of new information on imprecision levels. So we do see that imprecision changes, and I would say our results are fairly intuitive, right? Surprises make you less confident. There's an alternative robust Bayes model that I've alluded to that's supposed to handle imprecision. It does no better on 0.2, and it actually can't even give us this first prediction. And so we haven't figured this part out yet. All right, so imprecision and risk beliefs. One, vary substantially across people. Two, can be large even for high risk beliefs in a very salient problem. Three, predicts updating of risk beliefs in response to new information. And four, changes when people get better information. So here's an important question recently. I used to do this for COVID vaccines, but now I'm going to do it for measles, right? What is the effect of vaccination on the chance you get measles? Right? This matters because this is informing, right? So I just like tried to move up. I succeeded in moving up the appointment to get my son his next dose of the MMR vaccine because there's measles around here now. And so effectively this boils down to comparing two probabilities. The probability you get measles conditional on the vaccine and some characteristics, and then probability you get measles with no vaccine and then those characteristics. What matters is not the truth here, it's what people think it is, right? So this P sub I. So, one implication of this is that our ability to overcome vaccine hesitancy through persuasion depends on these imprecision levels, like how sure people are about these priors. So like maybe we could do this in a two-step process, right? So shifting priors can be hard, especially on polarized topics. Maybe we can move imprecision directly and make people more receptive to new information. So could be that a two-part intervention would work. Start by convincing people their existing knowledge is less certain than they thought, and then give them the new facts. So maybe that could work better than going straight to step two. We're trying to do both at once. I think it depends on the details of the belief formation process. Like how exactly do you go about doing this updating? It's plausible, this is the part of the talk that we sometimes call story time, where I just make up things that could be true. This would be neat to try. And that's it. Thank you so much. Yes.
Questions. And I don't have to just put on fire. What's the number one of that? First example, how you run it.
I mean, like, would just be undermining what people, like, where people think they're getting their information from. So start by the more I talk about this, the less it sounds like it's work, but just like start by making them doubt like where they're currently getting it. So if you think MMR like causes autism, right? Then like maybe you need to begin by like, pushing on where did you get that information from? Like, why do you think that's true? Yeah. Or sorry, wait, was that the end of the question?
Right, that's my question.
Okay.
But we sort of
Oh, yeah, sorry. So the question was, what does step one actually look like? Like, what would be an example of trying to do that? Yeah.
We can all go back to the HIV, and obviously, your main interest here is the theory about how, I'm really, I'm interested in specifics of HIV. And, there's long been kind of this conventional wisdom that, it's like, okay, people are overestimating the likelihood of transmission. Maybe that's not such a bad thing because, for public health reasons and such.
Yeah.
Yeah. Thinking about that. So where my question is for that particular example, I think those of us who work in this area, really, have struggled with the idea that people can't compound confidence, right? So very well, even people with a high intelligence. So there's the question of, okay, you have sex once with someone who's very positive confidence. If you have sex for a year, or whatever, and people seem to have very.
Can I write on this board?
Yeah.
All right. So
They don't.
Now a permanent marker.
Their answers, their
Is it?
answers to those three questions don't line up. And so I just wonder how all of this will work out if you asked different ones,
Variation.
yeah.
So the actual function looks like this. You can work it out from the binomial distribution. And then what people like think it looks like is, so if you take this, like sort of the thrust of the other paper that I alluded to about fatalism is if you take this, it turns out that there's a point at which like rationally what you should do is give up. And I think this is what like most Americans did with respect to the novel coronavirus, like, a couple of years ago, like Omicron comes through and like you sort of infer you're going to get this no matter what, and then you just stop caring. Like my best sense of how people think that this compounds is like something like this, right? Or maybe just like, let me do a third color. There's this paper called like Exposed Enough that has this like, documents evidence that what people do is like, they're like down here. And then after you like make enough mistakes, then you get it instantly. Both of those actually make the fatalism problem like even worse. Because people like rapidly, if you think about this, if you're purely selfish, right, then the marginal cost of more exposures becomes zero, right? There's no risk to you. And then people always want to ask about altruism. So if you're altruistic, like once you're HIV positive, so you think you're there, right? Then you can apply the same logic to trying to protect your partner. Like, is it worth trying to do something to avoid infecting my husband with HIV, right? And if it's costly to do it, then again, you can infer that the right thing to do is to give up. And unfortunately, it looks like a lot of people do that. So in addition to my paper, which is coming out in the Economic Journal, there's a new paper in AER Insights showing that if you literally just tested people for HIV back around the same time in the sort of pre-treatment era, then what they did if they tested positive was gave up on all other sort of health investments and they die at higher rates. And so this is not that HIV kills you, but literally like they have this randomized experiment where some people who are HIV positive get their results and others don't. And the ones who get the results die at higher rates. So that's a new paper by Rebecca Thornton, and my advisor, and Hans-Peter Kohler and a couple other folks. So, it would be nice if we could basically like lie to people, make everything sound scary and get them to behave. And I think the sort of the motivation for the project that data comes from is that really seems like it backfires sometimes.
That covers only one of our questions.
Yeah.
Like all of the sort of theoreticals we're talking about. Instead of asking about probability of transmission over the course of the year, was per act, or if you were asking about somewhat different one.
I I mean, the theory is there because I felt like we should be able to model this somehow. Oh, sorry. The question is, would this theory look different if it was like per act? I don't like, there's nothing in the theory that like depends on that in particular. I mean, except maybe, the other point about like, what's the imprecision in the likelihood. So could differ that way. I'm trying to get back to the models, and this goes slower than I expected. So yeah, I don't think that these theories are right. I don't think this is what people are doing. I don't think that it matches like the results all that well. Like it matches like some results, but not all of them. Like if anything, I take like our results in this paper as being like, well, I think we can reject that this is the right model of how people are doing updating. And like, I've never thought that actual humans were Bayesian updaters. And this reinforces my belief that they're not Bayesian updaters. And they're also they're not doing like robust Bayes either, right? They're not doing other fancier things that you could use to handle this kind of, ranges and risk beliefs. Yes.
So the model is fundamentally kind of tied to information and some presumption, privacy, our probability estimates, right?
Yes.
And so, one part of me was just thinking about the role of anxiety and the role of how people are kind of in context for something like HIV in Malawi is very different than in another place. HIV is also more anxiety provoking perhaps than the measles or
Yeah.
COVID now or something. So I wonder, I didn't have really a well-formed question, but I feel like I was just kind of intrigued by like how you think of our imprecision or our kind of fatalism kind of tied to how something might tap into underlying anxiety, underlying fear, underlying experience.
Oh, sorry. The question was, how does this like imprecision and or fatalism tie into anxiety about the disease? There's research about, like trying to sort of model, like fear, and like you can get sort of fatalism type results out of that. So one of the points of my paper back when it still had my fatalism paper back when it still had a model in it was to say, look, you don't actually need to have like anything beyond basic, like totally rational optimizing behavior to get this. But you can get it from those other places too. And yeah, I mean, these things are scary. I think people don't like to think about things that are scary. And that's part of why they end up not having well-formed beliefs about them, is they could go and get more information, but it's like not pleasant to do so. I don't know.
Anxiety would tell you the worst thing is going to happen automatically. And that's what you see in the original prior surveys, right? And surveys like that, like the worst thing is going to happen. And,
yeah. Well,
so I mean that's what anxiety tells you. So in these in these moments where we're talking about a very serious disease.
Yeah. So sorry, this comment was that anxiety tells you the worst thing is going to happen. That's also what the government of Malawi tells you in secondary school. So the only where you learn about HIV in secondary school in Malawi is a class called life skills. And I got the textbooks and read them. And the only thing that they say about like the actual like risks of HIV is this little like example story of a young woman who has unprotected sex one time, develops oral thrush like a couple months later. Then like her mom wants her to go get an HIV test and she refuses and like won't do it. And then finally like she agrees to go and she tests positive. And then she decides not to die alone, but to infect as many other people as possible. And then she passes away 3 years later. And the idea in this story of Nabeta is like, you're supposed to have a discussion about like, what did she do right and wrong? But like, it both like tells you these exaggerated risks about transmission. So it implies that you have 100% transmission risk, although it doesn't say that. It implies that your life expectancy conditional on HIV infection is 3 years, which is doesn't say that. It doesn't have like 1,000 people or randomly sampled or something. The actual life expectancy untreated is 10 years, right? And then it's also modeling like fatalistic behavior in a way. And so I don't think that you can like separate like the anxiety thing. But I also think like, you know, some elements of the strategy of scaring people about these risks were not done well, for sure. Yeah. Any other questions? I think we're technically out of time. Yes. Last one. So conditional on contracting HIV. So your mortality rate is about 10% per year if you have HIV and you don't have medication. So if at the time I did the study, nobody could get the medication basically, or they were just finally like starting to get it to basically pregnant women only. If you take the medication and then I think, you know, I don't know what the epidemiological or RCT evidence is. The HIV doctors tend to think that you go back to normal mortality. So effective treatment of HIV basically like keeps you alive indefinitely.
Thank you so much.
Thanks for having me.